Okay, so we're starting chapter 14. We mentioned the Sepper theory, and that's not this stuff. This is more quantum mechanics based. And one thing that's in the Schrödinger equation is we like to write the Schrödinger equation this way, just in general. Come on, guy. Now, what little piece of notation am I missing in this Schrödinger equation? The little hat on the operator. Right. So you solve this and you get the energies. And that's what they're doing to get this plot. Okay. They're solving the Schrödinger equation, just one orientation of the nuclei at a time. And all they're doing is they're taking two atoms, right? Like atom A and atom B. Or if it's homonuclear, it wouldn't be B again, it would be, what's homonuclear mean? A again. If it was homonuclear, right? If it was diatomic, that means two, but heteronuclear would be two different atoms. Homonuclear, same atom. But all they're doing is moving them closer and closer together. But the point is they fix this distance. They fix it at, I don't know, pick an R. Pick an R. It's fixed. And then they calculate the energy. And then they change the radius and they calculate the energy. Or you could make it more complicated. Have actual molecules there, right? And you're going to have an actual bond going on. So, but what they're doing is they're saying we can fix the nuclei position and just have the electrons do their thing. That's the Born-Oppenheimer approximation. That you can just fix the nuclei position and calculate energies because electrons are moving so fast with respect to the nuclei. Why? What's the difference between electrons and nuclei? Well, besides charge.
The size?
Not so much size as m mass, right? You take just one proton. A whole molecule has a lot of protons in it. But you take just one proton. How much more massive is it than one electron? It's 10,000. Look at the inside front cover. It's about 10,000. So that's just one proton. So these atoms, right, a lot more than one proton, unless you're talking about hydrogen. But even if you're talking about hydrogen, you still have 10,000 times the mass. So that's why they say this Born-Oppenheimer approximation really kind of works pretty good. And it is an approximation. So if it's not valid, then the curves you're generating here aren't going to be valid either. Okay. But so as you change that distance, let's say we get it to be RE on that plot. And then we get the lowest energy. What does that mean? Right? If you have that distance be RE, you get the lowest energy. Is that a good thing?
Yeah.
Yeah, right? Nature's all about minimizing energy. That's the natural thing to do. So the lowest, and also it's negative. What was the thought there of how you could have negative energy?
Giving it off.
Well, that's one way. We're talking about exothermic reactions, but that's not this. This is potential energy.
What about ionization energy?
I think ionization energy is positive. It's energy that you have to put into the system to kick out an electron. Why did we have? Because it's so odd. How can you have negative energy? It was their convention. These physicists.
Wow.
What did they say? They said that we're actually talking about what type of potential energy? Kind of like Ashley and Mikey.
Oh, because you were saying it's like attraction because
Attraction, yeah.
What do you call it? There's farther apart. Right?
Attraction, right? Because electrons are what charge?
Negative.
Negative. Protons are nucleus. So that was their convention. If it's repulsive potential energy, positive. Attractive potential energy, two different charges, negative. So that's So they're sticking to their convention. Okay, they're sticking to their convention. And if you bring things even closer and closer and closer, well, then look at the potential energy skyrockets, right, to be positive, because it's going to start repelling sooner or later. You bring stuff, right? You bring these nuclei too close together, yeah, they're going to start repelling. It's going to be like a wall, and that's what the plot shows you. It's a freaking wall. You can't. It's like this right here, this table, right? That's why I can't put my hand through it. It's positive potential energy. Electrons here, electrons there. You can't push it through. Okay.
So we said attractive is positive and repulsive is negative.
We've been saying that for a while. Okay. So this is how they get these potential energy curve plots. Okay. So they call this bond dissociation energy, DO, but I don't see that on the I don't see that on the plot. Right? Because this is DE. I don't know if your plot's very good, but that says DE. Okay. The bond energy there at some radius RE. Okay. So the first bonding theory we're going to talk about, you're right, actually the first bonding theory you ever heard was Sepper, but we're not talking about valence shell electron pair repulsion theory, right? Valence bond theory. This is the one where, do you remember hearing stuff like SP, SP3, SP2, right? Okay. This is called hybridization. And this is all valence bond theory ideas. Hybridization, promotion, those are all things that you're going to hear a lot. Hybridization, promotion. Those are terms you're going to hear a lot with valence bond theory. So each bond is formed by spin pairing in an orbital. What's an orbital?
It's where the electron density is.
The key word that Brad just said is the very first one he said, is where, right? Orbital is a location in space, right? That's what an orbital is. And then the rest of what he was saying is right on. High electron density, it's where electron spends its time. Okay. So this is our first bonding theory that we're going to really talk about. And they're saying that if you have like two electrons, right, you can't tell whether the electrons, which orbital these electrons are in. Like, what they're really kind of talking about is hydrogen, right? And you don't really know, well, I guess you'd call it, they have atom B though, so it's not really the same thing twice. Let's call it HCl or something, right? So you don't know which electron these orbitals are in. Okay, it's kind of like delocalized idea. Okay, so we're not really going to spend a whole lot of time on valence bond, but they do give some useful ideas that we're going to be following up on. One is this, that if you take the combination of these orbitals and the one where they're added, okay, and you plot out this, so this is the actual wave function, and you plot it out, actually you're not really plotting the wave function, you're plotting, so when I say wave function, I mean this. When I say this, what do I mean? Well, kind of, but this is the magnitude of the wave function, or you can kind of think of it as probability density, or heck, the orbital, right? This is the actual where the thing exists. So if you have atom A here and atom B here, and you have high electron density between the two nuclei, well, heck, that's a what? bond. It's a bond. That's all they're saying. If you have high electron density between the two, and they're saying that, hey, what's holding this thing together? Well, probably this nuclei is attracted to those electrons, and this nuclei is attracted to those electrons, so there's high electron density there. Okay. So that's their idea of chemical bond. We'll be following through with that idea a lot. So if you have a nucleus here and a nucleus here, and this electron density is symmetric between them. The electron density is symmetric between them. They call that a sigma bond. Okay. They call that a sigma bond. So then they're trying to say here that this valence bond theory works pretty good for hydrogen because here's the observed plot and the calculated plot. They match up pretty good. Okay, not perfect, but they match up pretty good. Again, homonuclear meant what? Two of the same atoms, like hydrogen, chlorine, nitrogen, right? That kind of thing. Okay. Oh, I don't have a pi bond, but pretty much.
So.
Yep.
I'm sorry. So diatomic is two of the same atoms too, also. Correct?
Homonuclear is. Diatomic just means two.
So I would say like H2 is diatomic.
Homonuclear diatomic. Anything with two atoms is diatomic. Homo means one. Hetero means different. Homo means the same. So what I'm trying to draw here is a pi bond, right? I'm supposed to be drawing electron density where and where? Not in the middle. Pi bonds, what they're going to do is they're not symmetric in between, above and below. Above and below the plane of the nuclei. And what pi bonds do is they're supposed to prevent what? Twisting, right? You can't twist that bond. You'd have electron density here, you have electron density here, above and below, and that would be a pi bond. Okay, and I think figure 14.5 looks a lot better than my drawing. It's on page 390. Okay, I didn't get that in here. So it's the term rigid. You can't twist it. You can't twist that bond would be good explanations for pi bonds. Okay, so we're still talking about valence bond theory. And I can tell because we're talking about promotion and hybrid orbitals. So for example, if I had a carbon, so again, this is valence bond theory. Carbon, let's see if you remember this. If I want to write the noble gas core notation for the carbon atom, what would you write? Noble gas core electron configuration for a carbon atom. Start with helium in brackets, and then 2s2 and 2p2. Okay, so what I want to do here is I want to hybridize carbon. So the first thing I have to do is promote one of the s's up to the p's. Right? So I'll end up with 2s1, 2p3. Now that's called promotion. Actually, would that take energy? Would that take energy? I say most definitely yes, because is it the ground state? No. So then it has to take energy, right? It has to take energy. Okay, so we promote it. So you end up with, right? If you like it better this way, right? But the idea is you get hybrid orbitals, sp3. How many of them? How many of them? Yeah, how many sp3 hybrid orbitals do you end up with? This is going to follow through on every theory we talk about, including molecular orbital theory. The number of orbitals that you start out with, you're mixing.
Oh, okay. So
is the same number you end up with. So we started out with how many orbitals are we hybridizing? 4. So we better end up with 4. Okay. And moreover, they're all identical. They're all sp3. All they're going to do is just be in different locations in space. So if you plot it out, it looks like a tetrahedron. That's what this is, a tetrahedron. Okay. And what I think is kind of interesting is this plot. Because this plot shows you everything. Because how does an sp3 orbital end up getting this shape? This is all in theory. This is just models, right? We're not saying this is exactly how a carbon atom looks. This is just the model that works. So how does it get that shape for electron density? Standing waves, constructive and destructive interference. That's what this ugly plot with all these colors is trying to show you. That if you, with constructive and destructive interference, you end up with that lobe there. You end up with our typical sp3 shape, okay? Because of destructive and constructive interference. Okay. So how do these things look? This guy's on page 393. Well, I found a website that'll show us some nice pictures, but in the book you can take a look at what an sp2 hybrid orbital looks like, or an sp orbital looks like. But I think this one is the equilateral triangle idea. They're all pointing towards the corners of an equilateral triangle. Okay. So everything up to this point was that valence bond theory. And if you look at the homework, well, there isn't any. So we're just going to keep going. Okay. So we're going to jump into molecular orbital theory. And the literature says that this is the theory of choice. This is what folks like to use a lot. When I say folks, I'm talking about chemists. All right, so molecular orbital theory. So now what we're talking about is you have a wave function. And this wave function, right, it's for all the electrons. So this wave function is right, you can find the electron density like this by calculating it, right? And where are the electrons? Well, they're delocalized. Nobody knows everything's just kind of thrown in a pot. And like each atom provided electrons to be putting these in these molecular orbitals, and we'll see the shapes. But the point is that everything is delocalized. I remember taking organic chemistry. I did not have a wonderful experience in that class. But I remember the only talk about delocalized electrons was with the benzene ring, right? They had these double bonds and they're conjugated. Well, with molecular orbital theory, every single bond is delocalized. Nobody knows whose electrons are whose. They're all just mixed up in a great big pot. Okay, so this is supposed to be the same as that. I guess you'd have to be a hiker to recognize these contour plots, right? Yeah, topographic maps, but that's okay. So they're trying to say it's the same thing. So what they're trying to say here is that this is a molecular orbital wave function. And how do you get it? Right? Big sigma is sum Ci Vi. Okay. So these are all going to be, why not? Let's just use those solutions to the Schrödinger equation for the hydrogen atom, or atomic orbitals. 1s, 2s, 3, right? We have them all, and they work for hydrogen. Let's just use them. And Ci is the weight. The weight that you're going to give that particular atomic orbital. Now, what I think is really, there's always something really odd about quantum mechanics that you just can't figure out, right? Like if I give let's say we're, I don't know, you guys reach a wave function. You guys reach an atomic orbital. And I want to weight you differently, give you different probability, right? So one of you guys has a gold quarter, right? But the odds are it's this guy right here. Because you and I all know him. I mean, there's a chance. There's a chance that you all have the gold quarter. But just given who this person is, you know he's got the gold quarter in his pocket. So we weight him with a 0.5, right? Or something like that. So then everyone else has their weights. I guess all the weights should add up to be 1, right? You would think since we gave him a weight of 0.5, you'd think there'd be a 50% chance that he's got it, right? No. With quantum mechanics, probability is calculated like that. So what's the probability of that gold quarter being in his pocket? It'd be 0.5 squared. It's a very odd situation here. So, and why? Quantum mechanics, a lot of aspects of it you just can't put a finger on. You just have to accept them because they give the right answers. It has been yet to be proven wrong. So, in this microscopic world.
So they found a formula, but they don't know why.
Well, if you stick to the microscopic world, we're really comfortable. We know why. But if you want to go to the macroscopic world, then you don't know why. There isn't that one book that you can pull off the shelf, the grand unified theory of everything, right? Not yet.
Oh, one more thing too. His 0.5 becomes 0.25, and everybody else has become less than that. So does everything not add up to 1 then?
Well, we need to normalize it. We need to normalize our wave function.
And that's when you come up with that coefficient.
So you'll have it'll work out. It'll work out in the end. It'll work out in the end. The point is that if you're going to play poker in the microscopic world, your idea of probability is just shot to hell. I mean, what the hell? It doesn't make any sense, right? Yeah, yeah.
No, now you only have 2.5.
But what's curious is that if you did play poker in the microscopic world, what he said, 5 aces. You and I know that's impossible. In the microscopic world, is that impossible? So, I mean, it's probably more likely than having 6 aces, but okay. LCAOMO. That's what this really is.
What?
LCAOMO. Linear combination of atomic orbitals. Molecular orbital theory. LCAO. Okay. So that's how they're getting their wave functions. Okay. So you can generate these wave functions. You can get a sigma orbital. All right, you can get a sigma orbital. It's just like we said, it looks kind of symmetric about the internuclear axis there. So this is an example of a sigma orbital. Okay. So if we take a look at, we were interested in carbon, right? So if you want to generate sigma orbitals, we need electron density between the 2 nuclei. Well, the only 2 atomic orbitals that will really give rise to that, if you take a look at them, are 2s and 2pz. That's why that's all you see here. Even though you have 2px and 2py to worry about too, well, they're not going to generate sigma orbitals. That's why they're just messing up with this stuff, messing around with it. Okay. So you have atom A, and you have atom A, you have atom B. So you have atom A's 2s and 2pz orbital, and you have atom B's 2s and 2pz orbital. What do these colors mean? See how one, in this 2pz, this one's dark and this one's light? What does that mean?
I agree with the density. It needs electron density.
What they're interested in is how do you get your final molecular orbitals in these funky shapes. It's going to be just like it was with valent bond theory, constructive and destructive interference. They're interested in the sign of the wave function. So that's all these different lobes mean. Pick it. Okay, I'm going to say dark lobe is always negative. Positive lobe is always positive sign. So that's what it means. So you just pick, it just means that the wave function has different signs. And that's how, because they don't want you to lose the idea that this isn't what things look like. We haven't added them up yet. We haven't got our interference effect yet. Okay, so you do that, and then you get your results over here. Okay, so now they're starting with some notation here. Now if you can see that, that says 4 sigma star, 3 sigma. Okay, so remember where our 2 nuclei are. All right, our 2 nuclei. So what do you think the little star means? If you notice where the 2 nuclei are, here's the 2 nuclei. What's the little star mean?
Oh, that's right. Not normalized. That's when we do it times itself.
It's all it is we're starting out with what orbitals? 2s and 2pz, right? That's what we're starting out with. Well, these guys have some, I don't know, I just think of the energy scale. I don't know, they're right around here and here or something, right? Just trying to put them in an energy scale. Well, if we hybridize these things, if we do molecular orbital theory, and we get our end results, our molecular orbitals, if that molecular orbital is higher in energy than where you started out, anywhere up here, you're going to give it a star. Right? Because it definitely isn't going to be bonding. It's going to be anti-bonding. It's got too much bloody energy. Right? So that's all it means, is that the energy level's way too high. Well, hell, it was better off. It was literally better off being separate atoms flying around or separate molecules flying around before they even reacted and bonded. So it doesn't sound very natural. Right? If you don't have a star, that means bonding. So that energy level of this molecular orbital must be where on the energy scale? Lower than the individual atomic orbitals that you're mixing here, that you're creating molecular orbitals with. Okay. So these are examples of, notice they have the sigma, because they're interested in the electron density between the 2 nuclei. And then they have pi. 2 pi star, and this one is 1 pi. All right. And again, scribble in your nuclei. Can you see why one is bonding and one is anti-bonding? Right. Why is that 2 pi star anti-bonding?
It's higher in energy.
Well, high in energy.
Too high
Yeah,
energy.
well, high in energy, yes, that's the verbal answer. But looking at the picture, why is that anti-bonding?
Because the electron densities are opposite of each other.
Yeah, they cancel out. They're opposite signs. So there isn't any electron density, there isn't any net electron density above and below the internuclear axis.
But we said
With pi, there's no star. Do you see electron density above and below the internuclear axis? Most definitely. They're the same sign. That's all you care about. You don't care whether they're both positive or both negative. The point is they're both the same sign. Negative, negative added up, you get constructive interference. Positive, positive added up, you get constructive interference. But not negative and positive. Right? Negative and positive areas, what is 0? I would just call it this: constructive interference and destructive interference. And they're standing waves is really how I envision these things. Like if you have what is a standing wave? Well, you could have Go to church, the organ, right? You have an actual standing wave with nodes and constructive and destructive interference inside those tubes. Or go in a swimming pool, but everything has to be in simple harmonic motion. In other words, when you're generating these things, you can't be going the same speed. You have to be going fastest in the middle, stop on both ends, right? If you're going to generate standing waves in a swimming pool, for example. Okay, so we have antibonding and bonding. Overlap density. So here they're talking about hydrogen again, the 1s orbital, right? And overlap density. So you take those two hydrogen atoms, they're 1s orbitals, right? You get constructive interference. That's what they're trying to say. You get an overlap density, or you get constructive interference in between the two nuclei. Okay. And again, that energy is going to be lower than the individual 1s orbitals. Okay, whatever your molecular orbital here that they're trying to show. Okay, your wave function, its magnitude. Okay. So again, bonding orbitals, the idea that, okay, well, your orbital has an energy lower than the individual orbitals that you were starting out with. Okay. So then you have, this is kind of repeating ourselves here, but if you plot the orbitals, you can get destructive or constructive interference, right? See how there's no electron density between these dots are supposed to be what?
Nuclei?
Yeah, the nuclei. And they're, I guess, in the reading, I'm taking this from the reading, and they're supposed to be hydrogen atoms, mixing 1s orbitals. Those are the nuclei, right? Okay. And here they're trying to say that this is why there's bonding. And remember, these are the nuclei. So it looks like they're what? What's the big blue blob between them? What's in there? Well, I wouldn't. They're in between. So well, they're electrons definitely. But if you want to give it a name, what type of electrons? I would call it sigma electrons because they're in between the nuclei. But the point is, that's where the electron density is. So, what charge do the nuclei have?
Positive.
Electrons? Negative. So they're attracted to the center. So that's the thinking of why bonds exist. Okay. And if you don't have, if this is the end result of your wave function, well, then you're not going to have any electron density between them. Well, now you don't have attraction, you have repulsion, right? Or they're really not saying repulsion, are they? They're showing that the nuclei are attracted elsewhere, other than the center. So it's really not repulsion. I was probably using the wrong words. They're saying that no, it's always attraction. The nuclei are always attracted to the electrons. So they're attracted elsewhere. So we shouldn't have used the word repulsion, I don't think. Okay. Sigma electron, that's just an electron in a sigma orbital. Anti-bonding orbitals, right? Anything with an asterisk, star, they're going to have higher energy than our individual orbitals that we started out with. Okay. In our linear combination of atomic orbitals. They're just trying to show a nodal plane here. But they kind of already did when they talked about this one. Okay. Nodal plane. So what they're showing here here's valence bond theory. If you wanted to see atomic orbitals. Okay. 5F, 2P, 2S. I always thought the 2S was interesting, because what's the center thing? 1s orbital looks like,
or the nucleus?
1s looks like this. They're not showing the nucleus here. This is just the orbitals.
So it's the 1s?
So this is 1s looks like. This is what a 2s looks like. It's a node. It's a node in the center. I thought that was kind of curious. 2p orbitals. Okay. So valence bond theory. And then you generate hybrid orbitals, right? Here's sp2. Remember how they're all going towards the corner of a equilateral triangle? There's 3 of them. So valence bond theory. But if we jump to molecular orbital theory, okay, so what are they doing? They're taking, let's back up a little bit. Molecular orbital theory. You take 1s orbitals, one from each hydrogen atom. This is what they look like. And then you combine them. So they have a little animation of what this is going to look like. Here's the bonding sigma orbital when they come together. So you get a sigma bond. But then you could also mix them and you get anti-bonding. All right, so they end up just looking like that. There's no electron density between them. Okay, so the static image would look like this. Different signs of the wave function.
Like how is that possible to like?
Well, the point is that in theory, we like to think of, oh, you have this 1s, and then you have 2s, and then you have 3s, right? Okay. Block all that out. You use that information to generate molecular orbital. Because now we're not talking, because when you say 1s, 2s, 3s, we're really referring to solutions to the Schrödinger equation for an atom, the hydrogen atom. So you can use those solutions for other atoms, I guess, and you won't be, I mean, you'll be off. But if you use it for molecules, well, heck, you don't even have atoms anymore. Now you have molecules. So what they're doing is they're taking these individual, they're taking the individual linear combination of atomic orbitals, 1s and 1s, and just combining them. Okay, now what are the, we haven't seen the plots yet, but we're going to be doing the exact same thing, just plotting out molecular orbitals. And we're going to have our 1s's, like maybe here, and then looks like we'll have a sigma star. Well, that energy level is going to be higher than our 1s's. And then we'll have a sigma orbital, and that'll be lower. And we have 2 electrons to fill, so we'll be filling them in with these molecular orbitals. And that's the thinking. So we'll be filling in electrons and orbitals. We just haven't generated the diagrams yet. We're just trying to get the idea that the 1s orbitals, whatever you're mixing, are here, and then bonding will be lower, anti-bonding will be higher. Okay. And how did we generate them? We generated them from 1s, 2s, all those atomic orbitals. Here is anti-bonding, mixing the p orbitals, right? Mixing these guys in the x direction, mixing 2 of those. That's anti-bonding, though. Anti-bonding. You want to see a bonding, it would be looking like this. The pz, because the 2 pz's are oriented in the right direction for a sigma bond. Okay. So that's kind of the idea behind molecular orbital theory and valence bond. Okay. So exercise number 8 and 9. Show that the sp2 hybrid orbital s plus the square root of 2p is normalized to 1. We should probably read the book, make sure this is looking right. Oh, I see how they wrote that. So show how this orbital is normalized to 1 over the square root of 3. Oh, it should be over the square root of 3.
14.88.
Okay. S plus the square root of 2p over the square root of 3 is what it's supposed to say. So that should be 3 to the 1/2. It's normalized to 1. That should be square root of 3. If the s and p orbital is normalized to 1. So what does that mean? If this comment is key to understand this question. What that means is that 1 would be the integral, like for s, it would just be s star s. Right? P is normalized to 1. What that means is 1, if you, that's 1. Okay. So what we want to do is we want to set up what integral and see if it equals 1. What integral do we want to set up?
The wave function for the SP2 vector?
Is normalized. Yeah. So how would you write this? How would you set this up?
1 equals integral n squared.
You want to show that it's normalized. That means you better get 1. We're not trying to normalize it.
Oh, so do we need the n from the?
Do we care about n? We want to show that something's normalized. Whenever you show something's normalized, what do you start out with? What's the general psi star psi d tau? Okay, what's my psi? Then we just substitute in to our expression, nothing extra, no n's, right? This is the normalization expression. They didn't say to normalize psi. Did it say to normalize psi?
Oh, it's already.
If it said to normalize psi, you put in an n.
Right. So just
Right.
when the wave function happens.
What is our wave function?
The S plus
There it is. Exactly. That is your wave function. Okay. So we have to put it into our expression.
What does the S stand for? Is that the SP2 one or the? That's the S one.
That's the s orbital. Well, there's a lot of math behind here that they're hiding, right? They're saying that the s and p orbitals, they're just calling it s. They're not having us put in all the ugly mess for it. Thank goodness, right? It's kind of like saying let s equal big blob of ugly math. Okay. So what would you substitute in next then? 1 has to equal the integral.
We would do that whole equation squared.
But what does this mean?
That's where we
Well, check up here, right? What does S star mean? Complex conjugate, right? Complex conjugate. This is because they said that S is normalized. So that's why I wrote this. P is normalized. That's why I wrote that. So if you want to write psi star psi and check and see if something's normalized, this is wrong. This isn't psi star. Right? Aren't we supposed to write psi star first?
Yeah.
How do I write psi star?
Would it be S minus?
Well, I guess you could do this, but it doesn't really make much sense to me. Where do you put these stars? All right. This is not psi star. This is psi.
So we're adding an I somewhere in there?
If you add an I, you're changing the wave function. I should not have given you this. I should have had you figure it out. If we say that S is, go back. If we say S is normalized, that means 1 has to equal the integral of psi star psi s d tau. And what is the wave function for S? It's just S. So 1 has to equal the integral of S star s d tau. Right? So, right? That's all you do. Make them complex conjugate.
So we're doing complex conjugates?
Yeah.
So then that should be S negative square root of 2p, right? Over square root of 3?
Yeah, if you want to make something complex conjugate, well, let's make it complex conjugate. It doesn't make any sense to put stars on the square root of 2 or 3. They're just numbers, right? This is, again, what they're trying to do is they're trying to make this math a lot easier for you. They're not giving you the S wave function and the P wave function. If they did, you're right. You'd have to replace i's with minus i's. There aren't any i's to replace here. This is just, they're giving it to you in general. So if you want to write the complex conjugate of the wave function, yeah, S star, P star, square root of 3. So this would be psi star.
So complex conjugate isn't where you take the sign and change it, like in calculus how they do that for finding.
Whoa, go wait. You forgot how to normalize things. If you want to normalize anything, and you have to have psi star psi, step the integral equal to 1. Okay. And if you get 1, it's normalized. But that psi star part, how did you write it? Because the psi, you always know what the wave function is. It's just some big ugly mess. How do you go, if you know what psi is, some big ugly mess, how do you write psi star?
Same thing.
Same thing, but replace what? With what? I with negative I. That's all you do. Are we replacing I with negative I? Essentially, we did. We just don't see it. Okay.
No, so because we're not actually using the equation, since we're only using one variable.
It's like
to
x.
describe the entire
Let x represent the wave function. Well, then the complex conjugate of x would be x
So
star.
then the wave function will have the i's and stuff in it.
Yeah, we don't want to go that. You do. Believe me, you don't want to go that far.
So we're just using like an algebraic representation to describe the wave function. So
Yeah.
the S star will represent
The complex
whole
conjugate,
function with
complex
the i's
conjugate
and the negative
with
i's.
negative. Yeah.
Oh, okay.
So now you have to multiply this through, right, and use these relationships, right? Wherever you get S star S, break up the integral into as many parts as you can. Where you have S star S, you'll have 1. P star P, you'll have 1. This whole thing is going to work out to be 1. Okay, so try it. So come by if you have some trouble.